Welcome to this video lecture, Eruption Styles Part 2, Forming the Volcanoes. As mentioned in the previous video, eruption style is dependent on both the viscosity of the magma and the gas content of the magma. These different magmas are going to erupt in different ways, resulting in a variety of distinct volcanic landforms at Earth's surface. In this video, we'll define a variety of eruption styles in more specific ways before going back to relate these eruption styles to their resultant landforms. To start with, effusive eruptions. As you know, these are eruptions of low gas content magma. Maybe that magma had a low gas content to begin with. For example, the magma is being erupted at the mid-ocean ridge, or maybe that magma became degassed as it rose up through the crust. Either way, the subsequent eruptions are characterized by lava. This lava can be very runny, as is the case here with this low viscosity and of course low gas content lava. Here is another example of something a bit more ropey, still quite low viscosity. Smooth, ropey lava like this has a special name, pahoehoe. It's a Hawaiian name. Pahoehoe lavas are low viscosity, low gas content lavas that flow smoothly over the surface of the Earth. Slightly more viscous, though still in the same low viscosity class, is aa lava. Pahoehoe and aa have approximately the same silica content, but due to changes in the steepness of the slope that they're flowing down, changes in the eruption rate, or differences in temperature, aa just moves much slower and more like a bulldozer, while pahoehoe flows smoothly like a fluid. Now, the surface of an aa flow is very different. It's broken, rocky, and sharp, very unlike the smooth pahoehoe flows that we see. Significantly more viscous than either of those are the lavas that characterize large subduction zone volcanoes. Here we find lava spines and lava domes, which are so thick that they hardly flow like a fluid at all. Instead, it's more like they're just the last little bit being squeezed out of a volcano, often at the conclusion of an eruption, kind of like squeezing out the last bit of toothpaste from the tube. Moving our attention from effusive to explosive eruptions, we can actually give different types of explosions different eruption style names. In this class, we'll restrict ourselves to just two, Strombolian eruptions and Plinian eruptions. Strombolian eruptions are the result of low silica magmas. It is believed that these low viscosity magmas enable gas bubbles to move up through the magma, expanding as they do, so getting bigger as it rises up closer to the surface. And eventually, these bubbles are going to burst at the surface, shooting out these globs of lava. And when they do, those blobs of lava will eventually cool down, and we call those particles, it's a volcanic hazard, a volcanic product, and we call those volcanic bombs. Volcanic bombs are any volcanic pyroclast about 10 centimeters in diameter or greater that are ejected from the vent while molten, and they cool down in flight. These pyroclasts, they actually, in this time-lapse photograph, you can see that they follow these beautiful sort of ballistic curves. So anytime you see a photo like this, it is a time lapse, and every single one of these little lines has one of these particles at the end of it. They typically follow those pathways and they land on the volcanic edifice. They land on the slopes where they'll either stay in place or roll downhill. These Strombolian eruptions are typically very small. They might last only a few seconds to a few minutes, although they can repeat maybe every hour for a significant period of time. This could go on for maybe a few days, maybe even a month or a year in some cases. Higher silica magmas are going to create more explosive eruptions because the gas within them cannot move as easily and has nowhere to escape to. These magmas have high gas contents and high viscosities. So when the gas bubbles within the magma expand as that magma approaches the surface, it comes to a point where almost the entire volume of the conduit is actually taken up by the gas. The white here is gas, and this fills the conduit and increases the pressure so much that it actually propels the ash and gas mixture up out of the volcano like this, creating incredibly explosive eruptions characterized by very tall eruption columns. These eruptions tend to be very large volume eruptions. They eject huge amounts of magma, primarily in the form of tephra, which is just any volcanic particle that has flown through the air, primarily ash, which is a specific type of tephra. They're characterized by the large sustained eruption columns that you can see in all of these images. These might reach tens of kilometers into the atmosphere. Occasionally, they even break through the troposphere and into the stratosphere. Primary hazards generated by Plinian eruptions include pyroclastic flows, which you can see here is this cloud of material that's actually moving downhill. These are incredibly deadly mixtures of hot ash and gas. The other thing that these composite cones are known for is hars, which is an Indonesian word for volcanic mudflow. The other common, though less deadly, hazard to come out of these is the ash fall. This is always a very huge, very significant portion of the eruption, and it can be quite dangerous because this stuff is very hard to breathe. It's very bad for you if you breathe it. It's like breathing rock. It can overrun sanitation systems. It's horrible for electronics, and it also causes roof collapse. Okay, now that we're familiar with a variety of different styles of eruption, let's see how each of these styles relates to the common volcanic landforms that we can see here. We'll start with shield volcanoes. Shield volcanoes have these really broad, they're very broad landforms, characterized by low slope angles, right? So they're not very steep at all. This is due to the fact that the magmas that create them have fairly low viscosity magmas that flow even under their own weight. So as these magmas are being erupted, they're just sort of settling down, creating these low slopes, broad volcanoes. And these shield volcanoes are primarily constructed during these effusive eruptions of low viscosity, low gas content magmas. So your pahoy hoy and your Composite cones, on the other hand, large, beautiful cone-shaped volcanoes have much steeper slopes because they are constructed from medium to high viscosity magmas. They build up by successive Plinian eruptions followed by lava eruptions. And this pattern of ash on the surface of the volcano, and then lava flows or domes creates successive layers inside of the volcano that are actually quite prone to collapse. So it turns out that landslides are also a very prominent hazard here. Eruptions at these types of volcanoes, well, you might have an effusive eruption following just a few decades after an explosive eruption, but it can be multiple hundreds of years between Plinian eruptions. Cinder cones are much, much smaller than either shield or composite volcanoes. They're so small that they can actually grow on the sides of both composite volcanoes and shield volcanoes. These are typically quite conical features. They have these large summit craters. Okay, so you'll have a fairly conical depression up here at the top. They are most often created by successive Strombolian eruptions of a period of just a few days. Here you can see a beautiful time-lapse photograph of some of those bubble wall pieces, which are just the little globs of lava just coming out and flying through the air to land on the volcano slopes and then go rolling down. Okay, these only look red because it's nighttime. If we were to see this during the daytime, it would actually be a bit darker than this. So even though the cones can be built in just a few days, they typically only erupt once and then never again. There's such small volumes of magma that the conduit completely seals off after an eruption. And if you're going to have another eruption in the same area, it's just going to go somewhere nearby instead of using the exact same volcano. So you often find multiple cinder cones in an area instead of just one. Finally, we have the other sort of smaller feature, which is the dome complex volcanoes. These high viscosity degassed lavas never travel very far from the vent, and instead they build up these quite steep domes, either directly on the landscape or also quite commonly inside of the slopes of stratovolcanoes. Yeah. So each volcanic construct is the result of one or more eruptions. The style of these eruptions determines the size and shape of the volcanic feature left behind. The viscosity and gas content of magmas are linked to the melt generation mechanisms of their plate boundaries where they are formed. These factors, viscosity and gas content, determine the eruption style, which in turn determines what volcanic feature is created as a result of the eruption. Or in other words, the eruption style determines the type of volcano. This concludes the Eruption Styles 2 Forming the Volcanoes video lecture. See you next time.